You are standing in a dark control room while a new world crawls onto a screen, one strip of light at a time. Pluto is the subject. If this tiny world is anything more than a frozen leftover, then we have misunderstood a whole edge of the solar system, and the next few hours could prove it. Stay close for stories like this, because the reward is not just seeing the picture first, but learning how to read the shock hidden inside it. At first, the image does not look like history. It looks soft, incomplete, a pale coin with smudges on it. But in rooms at NASA, at Johns Hopkins Applied Physics Laboratory, and at the Southwest Research Institute, people are leaning in the way people do when they know a quiet thing may become a loud one. Pluto had always lived in our minds as a faraway punchline, a dot at the edge, a world so small and cold that even its demotion from planet status seemed bigger than the place itself. And yet the first close looks did not make Pluto feel smaller. They made it feel like something stranger, older, and very much awake. What made scientists watch so closely was not just the beauty of the pictures, it was the feeling that each new frame was breaking a promise the solar system had seemed to make. Small worlds were supposed to be simple, far worlds were supposed to be still. Pluto was beginning to hint that both of those ideas were about to get hard to defend. To see why this matters, we need to step back. Most people think Pluto is a distant ice ball that was once overhyped, later demoted, and then mostly settled into the background as a cold, silent leftover. In that picture, Pluto matters for classroom arguments, not for live science. It feels finished before the story even begins. Pluto entered modern history in 1930, when Clyde Tombaugh found it at Lowell Observatory in Arizona. He was young, careful, and staring at glass plates for tiny shifts of light. What he found was not a bright new giant, it was a dim, moving speck. From the start, Pluto arrived with less glory than the name around it. Even after its discovery, Pluto stayed hard to love in pictures. Through most telescopes, it was not a world in the way Mars is a world, or even the way Jupiter's moons feel like worlds. It was a point, a stubborn little bead of light more than 3 billion miles away. For decades, if you wanted to imagine Pluto, you had to imagine almost all of it. That distance did something powerful to the public story. The less we could see, the easier it became to flatten Pluto into a symbol. It became the little planet, then the not planet, then the joke at the edge of the diagram, a place people remembered mainly because school posters kept having to change. Scientists knew a little more, but not enough to kill that simple picture. Pluto was found to have an odd orbit. It swings around the sun once every 248 Earth years. It is made of rock and ice. It has a large moon, Charon, and later smaller moons too. But none of that yet made Pluto feel alive. It just made it feel unusual. There were hints, though. In 1988, an event called an occultation let scientists learn something surprising without ever going there. An occultation is when a world passes in front of a distant star. As the starlight dims, it carries clues. Ted Dunham and other researchers used that fading light to show that Pluto had an atmosphere. Thin, yes, but real. That mattered because atmospheres are troublemakers. They move heat around, they change with seasons, they can grow, shrink, freeze, and drift. Pluto was suddenly not just a frozen lump, it was a place with weather-like behavior, even if that behavior was happening in brutal cold and slow motion. Still, it was easy to think of that atmosphere as weak and temporary. Then came the moon story. Charon was large enough, compared to Pluto, to make the pair feel less like planet and moon, and more like partners circling each other. Hubble later helped reveal 4 more tiny moons, Nix, Hydra, Styx, and Kerberos. That made the Pluto system feel busier. But busy is not the same as active. A cluttered attic can still be dead quiet. By the early 2000s, Pluto was in a strange place in science and culture. It was famous, but blurry. Important, but half dismissed. Children learned its name, and adults argued over its title, while researchers were forced to build entire ideas from thin slivers of data. The world itself remained hidden behind distance, glare, and patience. That is why New Horizons mattered so much. Launched on January 19, 2006, it was not a giant flagship mission. It was compact, fast, and built for one long shot. Alan Stern of the Southwest Research Institute helped lead the mission. The spacecraft would race outward for more than 9 years, cross billions of miles, and get one brief chance to see Pluto up close. A flyby like that is not a visit the way people imagine one. It is more like throwing a message through a closing door and trying to catch what comes back before the gap is gone. New Horizons could not stop, it could not orbit. It had to arrive at exactly the right moment, aim with exquisite care, and gather everything it could in a single rush. Even then, nobody expected Pluto to suddenly become one of the strangest places in the solar system. There were models, of course. There were guesses about ice, craters, maybe some surface patches with different colors. There was hope for complexity, because scientists are always hoping the universe saved a twist for them. But hope is not the same as expectation. Most people, and even many people who followed space news, still held the same basic picture in their heads. Pluto was far away, very cold, very old, and probably quiet. If it had surprises, they would be the gentle kind. A few ridges, a few scars, a little frost. The kind of details that sharpen a postcard but do not rewrite the map. The long trip itself seemed to support that mood. Year after year, Pluto stayed a target, not a place. The spacecraft kept moving through darkness. The signal time stretched. The data rate would be painfully slow. Even the drama felt thin and cold, like the weak sunlight that reaches that part of the solar system. Pluto still seemed destined to be more distant than startling. By the time New Horizons closed in, the prevailing assumption sat firmly in place. Pluto might be pretty. Pluto might be scientifically useful. Pluto might even have a few odd features worth a paper or two. But the core image held. It was still supposed to be a small, frozen remnant, a world whose best days were billions of years behind it. But that picture is about to change. What we have just taken for granted turns out to be only the shell of the story, and the shell is beginning to crack. Drop a comment with the exact moment Pluto stopped feeling small to you. That note helps this channel build the next deep dive around the details people almost missed. In the summer of 2015, the blur started hardening into a world. Scientists expected a better version of the Pluto they already knew, clearer, sharper, but familiar. What they actually got, as approach images improved, was a surface with bold contrast and a bright shape nobody could ignore. It felt less like cleaning a dusty window and more like opening a door into a room that had been lit all along. Then came the famous heart. Officially, the larger bright region is Tombaugh Regio, named for Clyde Tombaugh. Scientists expected a battered face, dark and old, like many ancient surfaces in the outer solar system. What they found was a bright, fresh-looking feature spread across a huge part of Pluto. It landed on the public imagination like a wink from a world nobody expected to charm. At 11:49 UT on July 14, 2015, New Horizons flew about 4,800 miles above Pluto's surface. The spacecraft had traveled for more than 9 years to get there. People expected that closest approach to be the climax. In a way, it was. But because radio signals needed about 4.5 hours to cross the Gulf, Earth had to wait in silence before the pictures even began to arrive. When they did, the first emotional shock was not just beauty, it was structure. Scientists expected Pluto's surface to show old damage everywhere, the way a long-abandoned object does. What they found were wide areas with very few craters at all. Jeff Moore at NASA Ames and others quickly saw the implication. Parts of Pluto's surface had been renewed. This was not a museum piece. This was a working world. Sputnik Planitia drove that point home harder than almost anything else. It is the western lobe of Pluto's bright heart, a vast plain of nitrogen ice about 1,000 kilometers across. Scientists expected an impact basin that had simply sat there frozen. What they found was a smooth, young plain divided into giant polygon cells. It looked less like stone and more like a slow pot of thick soup simmering from below. That was a hard image to shake. On Earth, when you see cells in a pan of oatmeal or tomato sauce, you know warm material is moving. On Pluto, the motion is far slower and the material is not food, but exotic ice. Still, the comparison helps. Beneath that plane, something was carrying heat and lifting material in slow churns over immense spans of time. Then the mountains arrived. Scientists expected low relief, soft slopes, and surfaces shaped mostly by impacts and frost. What they found were jagged blocks of water ice rising thousands of feet high near the edge of Sputnik Planitia. Water ice on Pluto is so hard in that cold that it acts like bedrock. The mountains looked young, steep, and raw, like shards of a broken shell pushed up yesterday, not 4 billion years ago. The surprise pattern kept repeating. Scientists expected nitrogen and methane ices to lie flat and inert. What they found were signs of glacial flow. NASA later highlighted these as some of the mission's most striking views. Broad, frozen plains, channels, and patterns showing that ices had moved and reshaped the land. It was like finding river bends in a place where you had expected only a locked freezer. Even Pluto's sky refused to stay simple. Before the flyby, researchers knew Pluto had an atmosphere, but many expected something faint and spare. What New Horizons found was a layered haze rising high above the surface. NASA images later showed around 20 haze layers in some views, stacked one over another over Pluto's limb. Instead of a bare black edge, Pluto had a delicate blue-tinted veil. That mattered for more than looks. A haze means chemistry. Sunlight is breaking apart molecules and helping build tiny particles. Those particles scatter light, move heat, and change how the atmosphere behaves. Scientists expected a thin gas envelope. What they found was a whole atmospheric machine, one that turned starlight and sunlight into a visible structure. It was like discovering breath in a place you had only expected frost. The shock spread to Karen, too. Pluto's largest moon was supposed to be the calmer partner, a grayer and simpler companion. What New Horizons found was a world with vast fractures, deep canyons, and a dark reddish polar region. Karen did not look like a boring rock tagging along. It looked like a body with its own broken history, possibly tied to an ancient internal ocean that had frozen and expanded. That ocean idea mattered because it pushed the story below the surface. If Karen once held enough internal warmth for liquid water under ice, then the Pluto system had a more active youth than many had imagined. Scientists expected a pair of cold leftovers. What they found was a family of worlds with tectonic scars, chemical stains, and a deeper memory of heat. The whole system suddenly looked less like debris and more like biography. Even the small moons misbehaved. In many moon systems, little moons settle into predictable rotations, always showing the same face to their planet. Scientists expected something neat and orderly. What they found from New Horizons data was chaos. Nix and Hydra spun wildly. Their rotations were not tidally locked in the simple way many people would expect. It was like finding toy tops still wobbling in a room you thought had gone still ages ago. As more data trickled back through late 2015 and into 2016, Pluto kept refusing to settle down. NASA's gallery filled out the picture with backlit crescents, high-resolution maps, and strange terrains. There were bladed regions east of the heart, like fields of giant knife edges made of methane ice. Scientists expected smoother frost deposits. What they found looked like a frozen forest of blades carved by slow, alien weather. Another mystery came with features called Wright Mons and Picard Mons. These huge rises suggested to some scientists that Pluto may have cryovolcanoes, meaning volcano-like structures that erupt icy slush instead of red-hot rock. People expected volcano talk to belong to places with obvious internal power. What they found were hints that even tiny Pluto might have pushed material up from within. It was like hearing a faint engine in a car long assumed dead. And yet the reveal did not stop at the flyby. One of the strangest parts of Pluto's story is that its atmosphere can be checked from Earth when Pluto passes in front of stars. On August 15, 2018, researchers led by Elliot Young of the Southwest Research Institute watched another occultation. Scientists had expected Pluto's atmosphere to keep thickening for a time, in line with earlier trends. What they found was evidence that its atmospheric density had begun to decrease. That change matters because Pluto's air is tied to surface ice. When nitrogen ice warms, it turns to gas and supports the atmosphere. When it cools, it refreezes and the air thins. Leslie Young at SWRI explained it with a beach analogy. Sand can stay hot after noon because it stores heat. Pluto had seemed to be doing something like that, but the 2018 results suggested the stored warmth might be losing its hold. The occultation itself even produced a central flash, a brightening caused by Pluto's atmosphere bending light into the center of the shadow path. Scientists expected a useful measurement. What they found was one of the strongest central flashes seen for Pluto. It was a reminder that this far world could still be tracked almost like weather, not by cloud photos from an orbiter, but by the way starlight warped as it passed through alien air. Then another window opened. After New Horizons, scientists had a world map richer than anyone expected, but they still needed new ways to test what that world was doing now. The James Webb Space Telescope provided that chance. In results highlighted in 2025 by a team including Shi Jiang and Linfeng Wan of UC Santa Cruz, along with researchers from the Paris Observatory and the University of Reims Champagne-Ardenne, Pluto revealed another layer of surprise. Scientists had expected Pluto's gases to control most of the atmosphere's heat balance in a fairly normal way. What Webb data supported was stranger. The haze particles themselves appear to dominate that balance by heating and cooling, shaping how the atmosphere behaves. Zhang had predicted this back in 2017, and the June 2, 2025 Nature Astronomy result backed it. That is not a small correction. It is a different operating system for a planetary atmosphere. The comparison helps here. Scientists expected Pluto's atmosphere to work like a room mainly controlled by the furnace. What they found was something closer to a room controlled by the curtains, where tiny suspended particles decide how heat is trapped and shed. On Pluto, those particles are made through chemistry involving nitrogen and methane. A haze, once treated as decoration, became part of the engine. Webb also separated thermal light from Pluto and Charon at 18, 21, and 25 microns, a part of the infrared spectrum that had never been explored this way for the pair. Later, a high-quality spectrum from May 2023 covered 4.9 to 27 microns. Scientists expected a modest cleanup of old uncertainties. What they found was chemical richness and thermal behavior that sharpened the questions about surface ice, temperature, and atmospheric exchange. And then there was Charon again. Researchers reported that material escaping from Pluto's atmosphere can end up on Charon's poles, where chemistry turns it darker and redder over time. Scientists expected two neighboring worlds, linked by gravity but mostly separate in daily behavior. What they found was one world quietly dusting another with molecules. It is like watching frost from one window somehow end up staining the frame of the next room over. By this point, the picture was almost too neat, and that is exactly where honesty matters. Scientists do not fully agree on every piece. They still debate how thick any hidden ocean might be, or whether one still exists. They still test how cryovolcanic some features really are. They still argue over the timing of surface changes and the exact role of subsurface heat. Pluto is not solved, it is opened. That uncertainty is not weakness. It is one reason scientists are watching so closely now. Pluto sits in a zone where small shifts in sunlight, ice temperature, and chemistry can change the atmosphere in ways we may actually catch. A world once filed away as ancient and settled is now being monitored almost like a slow experiment. We are not just admiring old images anymore. We are waiting to see what the next ones will mean. And here is where this stops being about one distant dwarf world and begins being about us. If Pluto can stay active, exchange material with its moon, and let tiny haze particles control an atmosphere at the edge of the solar system, then our neat categories were never as secure as they felt. Share this video with the one friend who still thinks Pluto is just a crossed-out planet on a school chart. Passing it along gives them the better map before the next discovery lands. What changes now is the way Pluto is watched. Not as a completed story, but as a live one. Scientists are no longer asking only what Pluto looked like when New Horizons flew by. They are asking what Pluto is doing across seasons, across years, and across wavelengths of light our eyes can never see. The mission turned a dot into a place. The follow-up work is turning that place into a system. That shift matters because Pluto is not easy to revisit. New Horizons was a flyby, not an orbiter. There is no spacecraft circling Pluto today, sending back fresh local weather shots every morning. So every new clue has to be squeezed from distance. Occultations from Earth, infrared measurements from Webb, careful reanalysis of the flyby archive. This is science done with patience, timing, and the willingness to learn from faint signals. In your own life, the closest comparison might be checking the weather through a bedroom window before dawn. You do not walk into the sky, you read the signs. Frost on the glass, damp air, a certain color of light. Pluto is like that, only slowed down across years and measured across billions of miles. Scientists are learning to read its seasons from subtle changes in starlight, temperature, and ice. One big unresolved question is the future of Pluto's atmosphere. Pluto has been moving farther from the Sun since its closest point in 1989. Because its ices store and release heat slowly, the atmosphere does not simply rise and fall with distance in a straight line. That is why the 2018 occultation result was so important. It hinted that the long rise seen before might have turned. If true, Pluto may now be entering a thinner air chapter. Another open question lives under the crust. Sputnik Planitia is not just a pretty basin. Some researchers have argued that its shape, location, and long life make more sense if Pluto has or had a subsurface ocean helping the crust shift and respond. That is still debated, but if even part of it holds, then Pluto belongs in a larger conversation about hidden oceans, internal warmth, and the surprising endurance of activity in small worlds. The surface is no simpler. Nitrogen, methane, and carbon monoxide ices move around Pluto with the seasons. Webb's infrared data sharpened the case that this redistribution matters. Some regions warm and cool differently. Some surfaces hold heat better than others. Karen may continue to record escaped material from Pluto. The pair are not just neighbors. They are participants in a shared outer solar system story, each preserving clues about the other. This is also why Pluto matters beyond Pluto. Shi Zhang of UC Santa Cruz has pointed out that haze-rich, nitrogen-heavy chemistry may help scientists think about very different worlds, including Titan and Triton, and even deep-time Earth before oxygen rose in our atmosphere. That does not make Pluto an early Earth copy. It does make it a laboratory. Sometimes the best way to understand home is to study a place that looks nothing like home at first glance. People often imagine scientific progress as a straight line of bigger and better pictures. Pluto's story is more interesting than that. A 2015 flyby gave us the shock. A 2021 report on 2018 occultation data sharpened the climate question. A June 2, 2025 Nature Astronomy paper used Webb results to confirm that haze can dominate Pluto's energy balance. Each step added detail, but more importantly, each step changed the kind of question scientists now ask. The numbers themselves tell the mood of the story. Closest approach came at 11:49 UT on July 14, 2015. The flyby altitude was about 7,800 kilometers. The heart-shaped Sputnik Planitia spans roughly 1,000 kilometers. Webb separated thermal measurements at 18, 21, and 25 microns, then pushed out to a spectrum from 4.9 to 27 microns. These are not decoration-level numbers. They are the edges of the net scientists are now casting. What comes next may not arrive as one giant reveal. It may come as a pattern. Another occultation that shows the pressure slipping. Another thermal model that better matches how the ice shifts. Another reprocessed flyby image that makes an old ridge look younger or stranger than before. Scientists are watching closely because Pluto has entered that rare zone where a far place can still surprise us in real time. There is also the question of return. Planetary scientists have studied ideas for orbiters and more ambitious missions for years because a world this complex is hard to exhaust with one pass. Nothing is approved for launch to Pluto right now. That is the honest part. But the scientific case did not weaken after New Horizons. It grew. The more active Pluto looked, the more it started to resemble a place worth going back to slowly. If a future spacecraft ever does return, it would not be going to settle the old argument about whether Pluto counts. That argument is too small now. It would go to watch nitrogen glaciers move, to map haze through changing seasons, to test whether cryovolcanoes truly reshaped the surface, and to look for stronger signs of what lies below. It would go because Pluto has crossed the line from curiosity to frontier. So what should you watch for? Watch for headlines about occultations because those tiny dips in starlight can reveal whether Pluto's atmosphere is swelling or collapsing. Watch for new James Webb studies because infrared light can expose how surface ices and haze handle energy. Watch for Karen too. If Pluto keeps leaving chemical traces there, the pair may keep telling a joint story. Even a distant system can behave like a conversation. And maybe watch your own instincts. The next time a small world appears in the news, notice whether your mind tries to shrink it before the evidence arrives. Pluto is a good warning against that habit. Scale can fool us. Size can fool us. Distance can fool us. A place can be smaller than our moon and still hold mountains, glaciers, haze, strange weather physics, and questions big enough to reshape how we think about whole classes of worlds. What happens tomorrow is not that Pluto suddenly becomes easy. It is that each new observation has more weight than it used to. Scientists know where to look now. They know which mysteries link together. Atmosphere, haze, surface ice, Karen, internal heat. The next useful clue could come from a planned telescope run, a lucky alignment with a background star, or a new pass through old New Horizons data with sharper methods than were possible before. Somewhere, perhaps on a quiet night at an observatory, Pluto will cross a star again. Somewhere else, a model will be rerun with better thermal assumptions. A student will compare a light curve to an older one and realize the atmosphere moved a little more than expected. None of those moments will sound as cinematic as a flyby, but this is how deep science usually grows, not in one shout, in a series of careful listens. And if those listens keep confirming what the last decade has hinted, then Pluto will stand as one of the best reminders that the solar system is not arranged by our intuition. The places we think are exhausted may be opening. The worlds we use as symbols may turn out to be systems. The faint object at the edge may be teaching some of the clearest lessons about how planets, moons, ices, and atmospheres really behave. Save this video and come back the next time Pluto makes news. That small habit will help you see the pattern for yourself, instead of only hearing the ending after everyone else has already decided what it means. So carry one image with you. Not the whole heart, not the whole globe, just that thin blue haze seen along Pluto's edge after New Horizons looked back toward the sun. A tiny rim of light around a distant world. It is delicate, almost whisper-thin, and yet it changed the way scientists think about heat, chemistry, and life at the far edge of the sun's reach. That is why I think Pluto's future will stay busy. Not because it will suddenly become easy to visit, and not because every mystery will resolve cleanly. It will stay busy because we now know enough to be surprised well. We know where the cracks in the old story are. We know which signals matter. And somewhere in the cold dark beyond Neptune, Pluto is still giving off clues, waiting for the next careful mind to notice them.